All right, so capacitors, when we add them up, first of all, we have our geometric argument of what is capacitor. Capacitor is, we got a constant. You have increasing area increases capacitance. Decreasing distance increases our capacitance. And you have some proportionality constant going on there. Okay, no big deal. We have our definition of a capacitor is something that provides us with an amount of charge per unit voltage. And the value of the capacitance is dependent on the geometry. This decides what C is. Once C is established, then we get this ratio. Give it more voltage, you get more charge. Okay, that's it. So if we have a simple circuit, once it is charged up, now when we first connect the battery, positive charge is going to flow to the terminal that is connected to the positive side, to the over here. So this is voltage. This is going to have a plus Q on this side. The side that's touching the negative terminal is going to get a negative Q. And this capacitor had a value C here, and the amount of Q is equal to C times V, because that's just rearranging this guy. Right? No big deal there. Now, we're going to go parallel first. In parallel, same rules apply as before. That is, they are all touching this terminal. These sides are all touching this terminal. So what is the voltage across all of these guys? Same voltage as over here. And we will pretend that we have nice, simple, easy voltage, which is no internal resistance, and it's the same thing as EMF if we wanted to put an epsilon there instead. All right, so that means charge 1 is equal to V times C1. Charge 2 is equal to V times C2, and charge 3 is equal to V times C3. Now, that is because they all share the same voltage, and so we were able to figure out what their overall charges are. Our equivalent capacitance, actually, I'm not going to write it that way. I'm going to say C sub P, because these are all in parallel, is simply equal to C1 plus C2 plus C3. And we could prove this. It comes from the fact that the charges all add up. If you have a certain amount of charge here, plus Q1 minus Q1 plus Q2 minus Q2 plus Q3 minus Q3, they've all got to add up to some total amount of charge. So Q, the total amount of Q in a parallel circuit is equal to the addition of them. And this comes from the basic statement that we've all got the same voltage. Same voltage everywhere. This is, by the way, charge is just our static version of current from when we had resistors. So back before, when we had resistors in parallel, current 1 plus current 2 plus current 3 added up to total current. Charge 1 plus charge 2 plus charge 3 adds up to be total charge. If we look at our other guy here, our series connection, I'm just going to do 2 of them, save a little time. Okay, capacitor 1, capacitor 2. I have my voltage V here. My capacitance 1 over C sub S is equal to 1 over C1 plus 1 over C2 plus blah blah blah. Again, plus blah 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 here in case there are additional ones. So now if I were to reduce this to an equivalent circuit, calling it a circuit just because the wires are connected. This would be C sub S here. This would be V, and I would get positive Q sub S on this side and negative Q sub S on this side, and Q sub S would be equal to V times C sub S. Okay, my equivalent series capacitance. Now, this tells me that positive Q sub S is the total amount of charge which is touching my positive terminal. That's this guy right here, isn't it? So this is going to be positive Q sub S. the charge based on the equivalent series capacitance. My negative Q sub S is going to be over here, touching my negative terminal. In between, you have an isolated conductor. What happens to an isolated conductor when it's close to something that's positively charged? It induces a negative charge. Take a wild guess what size? Q sub S. And over here, if it came, negative charge over here, oh, it came from over here. Oh, that's plus Q sub S. All right, so for on a series circuit, on a series capacitor things, all the Q's are the same. Q sub S is constant. It is the same everywhere. Okay, everybody gets the same charge. Just like everybody gets the same current in a series circuit with resistors. Everybody gets the same charge in a series configuration with capacitors. Everybody does not get the same voltage. V1, hold on one second. V1 is going to be equal to Q1 divided by C1. I'm sorry, that's Q sub S because everybody shares the same one. And V2 is going to be Q sub S divided by C2. Now I'm done.